they chose their own team names. And you'll see a lot of Coogs in the team names. So Water Coog is going to present to you about a green hydrogen plant in Texas. And we have Fugro who have given this problem statement in the room. So you're rooting for them, I guess. All right.
Which one? 10 minutes ago? Yeah.
So you can ask the question during breaks or afterwards. Yes, 2:30%. Yes.
Yeah.
Maybe you will stay away from the light. All right, ready whenever you are.
Just a quick check of this. So is it working?
Just make sure your cups.
Oh.
It's working?
Yeah. Yep.
All right. You can start.
Good afternoon, everyone. We are Team Water Coog here to present our idea on hydrogen plants in Texas. Texas leads the nation in the production of renewable energy such as solar and wind. And this helps us produce a sustainable solution for our problem. Hydrogen. Hydrogen is the number one element in the periodic table with its unique properties. It is 14 times lighter than air and 57 times lighter than gasoline. And hydrogen has created a lot of interest with its current aim as $1 per 1 kg hydrogen in 1 decade. And Texas leads the production of hydrogen with over 3 million metric tons of hydrogen produced every year. And hydrogen is not just a fuel, it's the future. Traditionally, hydrogen was produced with using different sources such as coal gasification, steam process reforming of methane. Here, this image shows the different sources of hydrogen production and the processes. Green hydrogen. Green hydrogen, as the name suggests, the hydrogen produced from the sustainable process of electrolysis, where the water splits in the electrolyzer to form hydrogen and oxygen as byproducts. And around 0.72 million metric tons of hydrogen is produced by electrolysis in Texas. And coming to our problem statement, we currently focus on the water scarcity concerns and choosing an efficient electrolyzer, as well as setting up a green ammonia plant. We use one of these Six Sigma tools, Fugro, for the understanding of our problem better, such as customers, suppliers, and the process.
So as mentioned, green electrolysis requires significant water. So how to tackle this problem? So what if we have water scarcity concern? So one of the ideas is to reuse the wastewater. So we can reuse the wastewater, and we need to treat that water coming from different sources. So we are planning to set up this plant in Gulf Coast region where we can have the source of wastewater. And we treat water in the initial stage with adsorption on site ketosane. So it's a biopolymer where we can treat this water to remove the heavy metals or chemical additives coming from industries. And we can use the pre-treated water to multiple effect evaporator. So we can further filter using multiple effect evaporator where desalination of water happens. And this water goes into the electrolyzer, solid oxide electrolyzer. So our aim also includes production of green ammonia. So the solid oxide electrolyzer requires high temperature. So it's a high temperature process where we also are looking for ammonia. So ammonia is a Haber's-Bosch process. It's one of the revolutionary process in chemical engineering. So with this, we produce ammonia, and the benefit of this method is it's an exothermic reaction, which releases heat. So we can reuse the heat, so heat recovery for this process. So it's like a recycling process where you're producing hydrogen as a feed to the Haber's process, and you are using the heat again in the electrolyzer. So we get electricity from renewable sources like wind and solar. And the main focus or the heart of this problem lies here in this thermal storage. So we are integrating thermal storage and hydrogen storage. So we use some part of hydrogen for ammonia production, and some part of hydrogen we store in metal hydrides. So metal hydrides, it's a growing field now. People are doing research. So these metal hydrides, this works on absorption. So this is also exothermic process. So when they store the hydrogen, they release heat. So that released heat we can store in the thermal energy storage. So during daytime you store it, and during nighttime you like transfer it to the metal hydrides for hydrogen again. So this stored heat, this can be used for multiple effect operators for water filtration. So there is a continuous flow of clean water into the electrolyzer. So which means we are producing hydrogen, and we are addressing both issues. We are storing energy, and we are producing hydrogen and ammonia. So Texas, renewable energy, every day is not a windy day, every day is not a sunny day. It needs to be stored. If you want to use it, you need to store it. So this is our block diagram of our process. And we have a demonstration of electrolysis, how it works in general. Yeah.
So the electrolysis, as you see, the solid oxide electrolysis, that's the heart of the process through which you get to see the green hydrogen. So what we are trying to see or try to understand the process, how does it work? So basically, if I understand this, this is my electrolyzer. So in the electrolyzer, you will be having three components: the cathode, the working electrode on which the oxygen will be found, the anode, this electrode on which the hydrogen will be found, which is the main product of this, and you have a reference electrode where you can fit in, and then you can use the steam from the Haber-Bosch process to come in, and then this has a solid electrolyte. Since it's a solid oxide electrolyte process, so that is a solid electrolyte inside this, and then when the hydrogen that we get, we can take this out and use it further to the metal hydrides process that Rohit explained.
Yeah. So we did energy and cost analysis of the entire plant, how it looks.
And so I would like to continue regarding the numbers, where I want to explain how is it minimum viable to even work with this problem and to even take this to the industry. So the numbers involved in, let's look at the conventional methods so that I can justify that our process is much cheaper and much effective and much less carbon footprint level. So we are gonna let you know what is the operational cost and the capital investment that is initially needed, which is basically $15 million for the initial capital investment, which varies from the conventional methods, where the basic conventional gold gasification requires about $300 to $500 million, and the SMR process requires about $3 to $5 billion. These numbers are pretty wild. So, if we can reduce this, then it's pretty viable in my sense. And if you're looking at the operational cost, it's not going to cost you a lot, because for a day you're spending $100,000, where in the bigger industries you're going to spend at least more than 500K, nearing $1 million, based on the demand of the product, where the hydrogen you need to produce to meet the quota. Next. And I'm also going to let you know how we are reducing the carbon footprint and making it the most effective solution which we can find compared to other existing solutions. So basically, the GWP stands for global warming potential. So this is our main goal to reduce, which is calculated per kilogram of CO2 produced per day. So the total tons which we are producing is 112 in our process, and the existing process produce more than 50,000 tons per day. So which it also varies from 50 to 80,000 tons based on the demand and how much we are producing. So that's how we are going to ensure and justify that this is the process where you can achieve the near zero carbon footprint. And continuing on.
As our project is mainly on electrolysis, we need electricity. So we thought of choosing any non-renewable energy source such as wind. So we basically took NREL website, where we've got a data set which looks like this, and we have almost 8,760 rows in each data set, where all the features are noted there. So initially we took 3 major cities. One is Houston, Austin, and Corpus Christi. But again, in that we took 2 data sets for each of the city. One is 2019 year and 2020, where the mean speed is 5.98 for 2019 and 6.32 for 2020. And I also mentioned the standard deviations of the wind speed.
So now I would like to explain what are the problems that we are trying to approach and solve using the machine learning. So the first is, if we are trying to build a wind or allocate the new farm, so first we need to select the good location. So what's the suitable location in the Texas? So in order to do that, we finally found a few data from the San Antonio, Austin, and Houston. So what is the right location to place the wind speed? So there are several factors that are affecting the wind power generation. So it's the height of the wind turbine. For example, if you assume this as the turbine, what's height from the, if it is the ground, and the height, if we assume 100 meters from the ground, so if it is height is 20 meters from the ground, what is the mean wind speed? What happens if the speed increases? What happens if the height increases? So analyzing all this helped us to find what is the optimal height for the turbine, so that will generate the electricity that is required for our process. So as we all know, as the height increases, the wind speed increases. But for example, if we have the height of 1,000 meters, the electricity produced will be higher. But in order to set up the 1,000 meters turbine, we need to also consider the capex, opex, and all the costs to make. So we analyzed using the machine learning algorithms and found 100 meters is the optimal height. And then we also created the simple user interface so that anyone can access. So there we have the options like selecting the location. So here we have the Houston, Corpus, Austin, and then based on the data sets, we have the option like selecting which year data set that you want to do, and then what's the turbine height. So if you want to check how much electricity does it produce, if the height of the turbine. So considering all these parameters, and we also have the slide bar to select the wind direction, speed, and all those, and then it gives all the data with respect to that. So how the wind speed changes with respect to time. So wind intermittency is the highest thing that we need to change. So we analyze all this data, and then what's the best time to carry on the electricity to the process, because we need the good electricity without any intermittency. Otherwise, it will corrode the electrodes. We also analyze the directions. For example, if you see, this is a windrows plot. So we can see that the most of the wind is coming from the north and southern region. So we can also analyze in what direction we need to place the turbine in order to get the maximum efficiency. So overall, with the machine learning, we are trying to do all these problems.
Yeah. So if you look at this problem and the approach we did, so it's like integrating the chemical engineering, and because it's a renewable energy source, we are using machine learning to analyze the data properly. So it's an integration of different subjects and aspects. So we really thank our mentors who guided on this, and ready for questions if you have any. Thank you.
Maybe just a high-level question. If you were just to summarize what the cost of production for ammonia is of this green process compared to one that uses traditional steam form, what's the difference for your location per ton?
Yes. So in this, so we need to consider different factors like how much wastewater are you giving as input. So in this, we consider like it's around 70,000 gallons per day. So if we take that as a feed flow rate, so we are producing 24 tons of hydrogen and 136 tons of ammonia. So it's in a sustainable process. Whereas so the main factor again, it's an integration process. So we are not just producing ammonia, or we're not just producing hydrogen. We are storing the heat, simultaneously producing the ammonia. So if you look at the numbers, so this $15 million what we are presenting here, so this can be true for conventional processes, but it's just for the only single operation of, let's say, ammonia or hydrogen production. So here we are combining 3 factors and reducing cost as opposed to like traditional methods. So it will be higher. So short answer is it will be higher. Like as he mentioned, like it's around $100 billion dollars to set up a plant like this in larger quantity, like production of ammonia in larger quantities. Yeah.
Maybe I'll follow up on Scott's question, right? So I like the idea you gave that vision of 111, right, in a decade. How close are you to that?
That's a good question. So this is like futuristic idea. So this is a long-term process where like this integration, like storage of heat can't be done in a day, right? So like we need a lot of heat to store, and we need to consider so many factors. And again, location, and again, the intermittency. So all these factors, like environmental factors, cost, like economic factors, play a huge role. So we did this. So in our, like, we believe this is a good idea, like good approach to set up a plant like this. But then we need to consider so many factors. But if it is true, like if this can be taken into the industrial setting and start working on this idea, I think the 2030 vision, we are close to that, like maybe in a span of 5 years.
Okay, no question.
Okay, thank you very much. Thank you. The next team comes up. This